have a meeting and getting associated with 10-year anniversary. And so that would definitely be the goal. My sky here is gendered to AI. It's all good. Nice.
La de ese lado. Sí, ahí acabo. Sí, casi.
Sí.
Comenzamos en 2 minutos, gracias. Hola, ¿qué tal? Muy buenas tardes a todos. Bueno, vamos a dar comienzo a este coloquio muy especial aquí en el Instituto de Astronomía. en Ciudad Universitaria. Voy a cambiar el idioma inglés. So, hi everyone. So today we have our first colloquium of this series of distinguished speakers, and we have a very important person today with us, Professor Jordan Goodman. I will read about our speaker today, and then I will let him the floor. So Professor Jordan Goodman is a distinguished university professor and the former chair of physics department at the University of Maryland. His area of research, particle astrophysics, studies cosmic radiation to better understand the properties of elementary particles and the processes in space that produce these particles. This field blends elements of high energy physics and astrophysics, starting with his PhD work, which shown evidence of an abundance of heavy elements such as iron in high energy cosmic rays. He has worked to understand the nature of cosmic rays which hits the Earth. Previously, his work has concentrated on two experimental efforts, Milagro and IceCube. He is now the principal investigator and the US spokesperson of the HAWC Gamma Ray Observatory, and he is a UMD Distinguished Scholar Teacher and Distinguished University Professor. Jordan, thank you very much for being here today. The floor is yours.
My pleasure. Let me correct the fact that I'm no longer the spokesperson for HAWC, but I am the PI. And I have a few, and forgive me for speaking quickly in English, but I do my best. So the first time I ever came to Mexico, the first place I ever spoke was in this very room when we talked about an idea to build HAWC, and that was in 2006. So what you see here today is the culmination of that work, and I want to stress that when I say this is for the HAWC collaboration, I am presenting the results of the work that's been done by everybody to produce this experimental result. And it's been an extraordinary journey to do this. So this first picture, by the way, is some of our results pasted on top of an AI-generated picture of the HAWC experiment, but we'll get to that. Anyway, so why would we want to study high-energy gamma rays from space? And the answer is that gamma rays travel in straight lines, and they travel, let's get rid of my, so I can see my slides here. They travel in straight lines, and they aren't bent by the magnetic fields in the galaxy or intergalactic space. And we'd like to understand the origin of the highest energy particles, so we want to look up in space and see where they come from. And we want to understand the acceleration mechanisms. How do we accelerate high energy particles? Okay, let's see. So, what astrophysical processes accelerate particles to PeV energies? So PeV is 10 to the 15th electron volts. That's the energy scale we're talking about. So when we look for really high energy, we're looking at gamma rays that come from these things that may be an order of magnitude lower, but we're talking about processes that make things at 10 to the 15th electron volts. And these things come from shock accelerations, plasma shocks in extreme environments, and they come from objects like pulsar wind nebula, supernova remnants, jets from black holes, binary systems, and even active galaxies. And all of these things are targets for the HAWC experiment's investigation. So what actually produces high-energy gamma rays? Typically, there are two mechanisms that you think of to produce high-energy gamma rays. One is from collisions of hadrons, protons hitting nuclei or protons hitting protons, that create pi zeros that decay into gamma rays. So that is hadronic production with hitting something near the source or hitting something in intergalactic space or in the galaxy. But high energy electrons can inverse Compton scatter. So when we think of Compton scattering that we've learned about in school, we usually have a photon that comes in and hits an electron and the electron goes out. Inverse Compton scattering is a high energy electron comes in and scatters off of a photon that accelerates, that it changes the energy of the photon up. So that's inverse Compton scattering. And a lot of the processes we'll talk about involve inverse Compton scattering. But here's the key thing. If you want to get gamma, and where is this inverse Compton scattering off of? At the highest energies, because of relativistic effects, the only thing you can scatter off of is the CMB, the cosmic microwave background. And so we'll talk a little bit more about that. Oh, okay, got the buttons the right direction now. Okay, So I'm not, oh, too fast. I'm not going to talk about all of our recent results. I just want to point out that we have a lot of recent results in a lot of different areas. And we have things from, I will talk about our updated sky maps, our improved angular resolution, gamma hadron separation, what the highest energy sky looks like, TeV halos, I'll tell you what they are, binaries, including micro-quasars in the galactic center, and I'll probably wind up getting to TeV gamma rays from the sun, which is a really bizarre thing which we did, which is really cool. So, and feel free, if I say stuff you don't understand, ask anytime, just shout out a question, all right? And if I'm talking too fast, just wave and I'll try to slow down. Okay, so HAWC. Okay, oop, I don't know what that happened there. I think we just got restarted somehow. Let me just do this way, I know what I'm doing. Okay, so HAWC is part of this campaign of multi-messenger astronomy. So when we think of astronomy, or the Astronomy Institute here, you know, we often think of multi-wavelength astronomy, everything from, you know, radio to X-rays and this kind of thing. And gamma rays fit into that picture and is part of the multi-wavelength. But now we actually have two other messengers which are being used for astronomy. We have gravitational waves and neutrinos. And I worked for a while on the IceCube Neutrino Observatory. But this particular picture here on the right is a picture of the sun taken from the Super Kamiokande experiment, which I did work on also, from 2 kilometers underground using neutrinos. So we can look at astronomical objects using various things. And again, HAWC fits into this picture of doing multi-messenger astronomy. So let's start with the discovery of cosmic rays, because talk is kind of about cosmic rays. And in the early part of the 20th century, people knew about ionizing radiation. And they knew that if you took and you charged an electroscope, you think of the little things, and you brought some ionizing radiation near it, it would discharge the electroscope. But they didn't know where the radiation was coming from. So one of the ideas they had is maybe it was coming from space. So they decided they could shield themselves by going into holes in the ground, which were railroad tunnels. And what they discovered was railroad tunnels are radioactive. So there was a lot of radiation in the railroad tunnel. So they said, okay, well, maybe there's still radiation coming from space. They could go to a high mountain, but you're still standing on the rocks. So Victor Hess, in a series of balloon flights from 1911 and 1912, took his electroscope and he went up in the atmosphere, and he discovered that as he went up away from the Earth, the rate of radiation went down, but as he got higher, suddenly it started increasing. So he discovered what he called cosmic radiation or cosmic rays. Okay, and so this is the picture of his balloon. His electroscope was much better than this one, but he had his group of graduate students like all of us. Okay, and you'll notice that here this guy is going up to do an experiment in space, and he's dressed in a coat and tie, and I'm speaking to you, and I'm not. Okay, so the times were different. Okay, but anyway, he did this, and he discovered cosmic rays, and that was more than 100 years ago. And we know a lot about cosmic rays in that 100 years. We have measured the spectrum of cosmic rays over 12 orders of magnitude in energy, starting from, basically the lowest energy ones that make it through the Earth's field, out to an extraordinary above 10 to the 20 electron volts. And what's extraordinary is this thing looks like a straight line. Maybe it's got it on a log-log plot. So this covers 32 orders of magnitude in flux and 12 orders of magnitude in energy. And it looks kind of like a straight line. Now, the thing is, it actually isn't a straight line. There's some features here. One we call the knee, one we call the ankle, one we call, the foot. You can't see it on a log-log plot unless you multiply it by the energy cubed. Once you do that, you can see that it really does have features. Okay? And we think these features are related to stuff that's produced in our galaxy, escaping from our galaxy, and coming from other galaxies at the highest energies. So the one thing we don't know, though, is we really don't know the origin of all of the highest energy particles. 107 years later, or 112 years later, it's still a mystery. So why not just do astronomy the way everybody does astronomy, which is look where they're coming from, right? I mean, that's how you do astronomy. The problem is that these particles that are coming at the highest energies are charged particles. And so if this is our galaxy and we see a particle, and here we are at UNAM, and we see a particle coming to us, we may not know where it originated because of being bent in the magnetic fields. So we can't use charged particles unless we go really high energies. And people are trying this. So you can use other messengers, you can use neutrinos, you can use stuff above 10 to the 19th, but they don't really, there isn't very many of them. So the idea is to use neutral particles and to look for, and then one of the neutral particles are neutrinos, which again are rare, or gamma rays, which are actually relatively plentiful. So since gamma ray astronomy began, or very high energy, TeV gamma ray astronomy began, and I was actually present in 1989 when Trevor Weeks announced the discovery of the Crab Nebula, which was the first TeV gamma ray source seen with the Whipple telescope. Since then, we've discovered about 210, depending on what day you look at the source, of these gamma ray sources. And this galactic plot that you see here, what you see in the plot is that the vast majority of the sources lie along the galactic plane here, except for these pink things. And they are other galaxies. So typically what you see is there's a lot of objects that are in our galaxy, and there are other galaxies shining that we can see. And typically those other galaxies, so in our galaxy, we see supernova remnants, we see binary systems, but mainly what we see out of the galaxy are active galaxies, which have jets of particles, and we call those galaxies blazars. Now, I like to tease astronomers that they have different names for things depending on what orientation they are. So if my name was Jordan this way, I might have a different name if I was facing this way. Okay, well, it's certainly true of active galaxies. They're either radio galaxies if you're looking at them from the side, Seaford galaxies if you're looking at an angle, or blazars if the jet's pointing towards you. But they're all the same object. Okay, and we've even studied gamma ray bursts, which I don't have really a lot of time to talk about, but it's really an exciting thing, which is the most energetic stuff in the universe. So how do you detect TeV gamma rays? The problem is the flux of TeV gamma rays is too small to be seen with satellites. A satellite is this big, okay? And if you look at it, they're too small to really see high energy things. They can detect stuff up to a TeV, but beyond that, they're too small because the flux drops too quickly. So the two main techniques, which we can talk about, are atmospheric Cherenkov light, and I'll talk about Cherenkov light, where we look up on dark nights with telescopes and look at the flashes of Cherenkov light that's seen coming from these objects, and we use very large segmented mirrored telescopes that point and have a small field of view and work on dark moonless nights. Or we can do cosmic ray showers and detect the particles that actually make it to the ground. And this is what HAWC is, something that does this. So let's look at an air shower. If a proton comes into the top of the atmosphere, it will interact with a nucleus of nitrogen or oxygen, and it will undergo a hadronic collision. And in that hadronic collision, most everything produced are pions. And the pions come in three flavors, plus and minus and pi naught. And the pi naughts decay instantly into two gamma rays. And then the gamma rays move off and propagate through the atmosphere because it's highly relativistic. And those gamma rays produce an electromagnetic shower. They do this by the process of pair production and bremsstrahlung. And so in this picture here, the electrons are the green things that you see kind of everywhere. And the pions can do one of two things. They can interact again, produce more pions, which produce more pi zeros and pi pluses, or they can decay into muons, and those muons travel down to Earth. And the shower develops typically at about the height of an airplane flying, is the maximum. So what is this Cherenkov light? So Cherenkov light was originally proposed by a guy named Cherenkov in the 1880s. And he realized that if you had a relativistic particle moving through a transparent medium, that you'd get a shock wave, which was light. This is the same phenomenon as a boat going through water producing a wake, or a plane going through air faster than the speed of sound. So this shock wave propagates forward. If we look at the wake of a boat, we think of it as the cone of light, but we tend to draw light as rays, so it goes forward. Okay, and this is Cherenkov light. And if you walk about 100 meters from my office, you can peer into our nuclear reactor, and it looks like this. Interestingly enough, you may ask, why do we still have a nuclear reactor? Because it's too expensive to get rid of. Okay, just inside. But anyway, you can see the Cherenkov light. It's really pretty cool. And so the idea is, we built this detector based on it, and I'll talk to you about how it works. But first I want to talk to you about the collaboration. So this was a picture taken in November in Puerto Vallarta of the collaboration. The collaboration consists of a number of universities in the United States, and significantly, it has a very large contingent from Mexico, and in particular, UNAM, and in particular, the Institute of Astronomy. So, they've played a vital role in the experiment. We have lots of Mexican universities, and we have Max Planck Institute, and we have institutes in Poland, and so we've sort of propagated out. We also have China, which I haven't actually put on here, where our postdocs graduate and form groups and move out. And so it's been a very exciting experiment to work on. It is located near the Pico de Orizaba, which most of you will know where that is, but it's near, it's not far from Puebla, which Puebla is, I've discovered, either 2 hours or 4 hours, depending on how the traffic in Mexico City is from here. Okay, last Friday night it was 4 hours from here. Puebla, not the experiment. Okay, but we're located at 19 degrees north, and we're located at an elevation of 4,100 meters. So here's the experiment, here's the there, and another view which I really like, which you can see from an airplane, where you can see the Pico de Orizaba and the Sierra Negra. And our experiment is located in the saddle between them. And one of the reasons that we were able to build this experiment here was there was some existing infrastructure. The large millimeter telescope is located on the Sierra Negra, and there was an access road, and there was internet structure and things that went up the road. And so you can see that the LMT, or GMT as you would say in Mexico, is here, and HAWC is here, and the Pico de Orizaba is there. So this is a picture I took a number of years ago of HAWC before we finished putting out our outriggers. I would point out, to give you some scale for this detector, here is a very tall German fellow walking here. Okay, so these are very big tanks. This last week, we took people who were proposing the next generation experiment to go see it. Each of these water Cherenkov detectors is a metal tank with 200,000 liters of water in it each. The full detector was inaugurated it's hard to read that, I'm sorry about that. It was inaugurated in March of 2015. We decided this morning that we will have a 10-year anniversary this coming March in 2025 in Puebla. And it took 13 tanker trucks of water to fill each tank. So 3,900 tanker truck trips up the mountain to fill this detector up. Inside each of these tanks are 4 photomultiplier tubes, 4 light sensors. Inside they have purified water. It's got a cover over it, which you can see here, but it's light tight inside of the cover. And this is what each detector looks like. And again, to give you some scale, there is a, they're 5 meters high, they're 7.3 meters across, and they have this giant bladder inside that's light tight and positions the phototubes and holds the water. Now, building them was kind of fun. They were made of segments that a person could carry. Here's a person carrying one. And this is kind of how they were built. Right, there's my scale again. They were built, weirdly enough, from the top down. You think that's a strange way to build a tank, but that's the way we did it because we didn't want people working up in the air. So we built the first layer. I'm going to actually show you a video. I'll show you 3 videos. So the first thing we wanted to do is dig a trench. And then we went around with a laser level and leveled the trench. And then we put in these jacks. And then we went home for the night. Okay? And then the next morning we came back. And we assembled the upper layer, put the roof and the geotextile on it. And then we jacked it up. We went to lunch. And then we came back and finished building the tank. And then we went home for the night. And it's still sitting on these wooden blocks at the bottom here. And the next morning we came back and we buried it. And the burying is for earthquakes and protection like that. Okay, so that's how we built these tanks. And here's kind of a little video that shows you what the site looks like, taken from a drone. This is around the time of our inauguration. I probably should have optimized when I shared my screen for video, but it's close enough. You can get a sense of what it looks like. You can see the volcano. The building on the right is, the building in the back there is our water purification system and thing. In the middle is where the electronics are. And it's a really impressive site. Okay. So what do we do with this thing now that we built it? How do we actually detect gamma rays? Well, the idea is that one of these showers comes in and interacts in the atmosphere, and it's either a proton-induced shower, which has lots of hadrons and other stuff, or it's a gamma ray-induced shower, but it's moving at the speed of light, and it comes down and hits our detector in almost a plane. And if you look, you can see the shower move across the face of the detector. This is obviously slowed down by 1 billion, but okay, it moves across the face of the detector, and we can get the direction from the timing. So that's how we do our direction. The problem is most everything that hits our detector, 99.99% of the stuff that hits our detector are hadronic-induced air showers, and they don't point anywhere. So we have to figure out how to get rid of the hadron background that's everywhere. And so the problem is we have to take advantage of the fact that this shower here, which is hadronic, it has all this electromagnetic stuff. How do you distinguish the difference? So I have a feeling for those of you in the room, this will show up better on the monitor than the screen. But let me show you this. This is quite cool. So here we have, it may show up. On the left, we have a gamma ray induced shower, and we're going to start at the top of the atmosphere. And on the right, we have a hadronic shower. And if you look, you can see particles. The little blue dots are the electrons and positrons. In the hadronic shower, you can see a stochastic interactions where every once in a while the main core interacts. And you can see the gamma ray shower is very symmetric, and the hadronic induced shower is lumpy. And you see things, and you see those yellow dots are muons. And so we basically get to the point where we want to be able to distinguish that shower from that shower. And it's not that hard, because this shower is symmetric and doesn't have muons, and we can hopefully pick that up. So in our simulations, we can show that gamma ray induced showers are very smooth and don't have much outside of the center region, where hadronic showers have stuff outside, well away from the center of the core of the array. And so we've developed algorithms that look at the clumpiness of the shower and say that's a hadron, or we see the smoothness of the shower and we say that's a gamma ray, and we can just, and the more detectors go off, the more we can distinguish this. So we're able to do quite well. As a matter of fact, a little water here. This one's hot because it's been sitting right next to the projector. Okay. So we have something called a Q factor. And Q factor is just, if you look at a signal, you might look at the number, the excess over the square root of the background. If you have background showers and you have a signal, the number of standard deviations you might think is just this, the standard is the signal divided by the square root of the background. And so if we plot that Q factor with our new PAS5 reconstruction, depending on the energy, we can get factors of, at the highest number of detectors, hit 40 or 50 in Q. That's over the square root of the background. So extremely good significance for high energy showers. We can also get angular resolution. Our angular resolution is not good when you just hit a few detectors. But if you hit a lot of detectors, our angular resolution now can get down to about 0.1 degrees. So when we talk about, I'm going to talk a lot about this thing, PAS5. So we started with different reconstruction algorithms, and we kept improving them, and now we're at PAS5, which is now the best we have. And this is our sky map with PAS5. So this is looking up from the ground. I'll show you in galactic coordinates. You can see an extreme number of sources along the galactic plane. The galactic plane, I will remind you, probably don't need to, but the galactic plane goes from, goes from up here, down here, back that way. So these things are just slightly off the galactic anti-center. Okay, and if we plot these things, and here's some AGN sticking up here. There are active galaxies that we see as well. So if we plot this in galactic coordinates, we can see that because we're at 20 degrees north, 19 degrees north, we can see out about 50, to about 45 or 50 degrees. So we can't see past 70 degrees north, which is why there's a hole at the north. You can't even see it on the screen, but over here you can see it. Okay, there's a hole at the North Pole, and there's a hole in a large region at the South Pole because we can't see the southern hemisphere from Mexico. But what we can see is a lot of interesting things, and I will show you. We're going to see there's the galactic center is here, the galactic anticenter is here, and we're going to talk about these things a little bit as we go along. And I'll show you in better color scale some things you can see. So to just give you some sense of the difference between our previous past and our current past, this plot shows you what approximately the same amount of data looks like and how our angular resolution is improved and how much sharper it looks in our new data pass. You can see things much, much more clearly in our new data pass. So let's look at the galaxy, all right, and blow it up a little bit. All right, so just to give you some scale, this is the number of sigma, if you like, or standard deviations, or the square root of the test statistic that we get. And the black is there, but then the green lines are, and I made this plot, I think we're 10 or more. So this is, goes up to about 50 sigma. This is about 60 sigma, extremely high detections. But let me show you a few things we're going to talk about in this galactic plane. So this goes from, this starts at the galactic center here. Okay, we're going to talk about the galactic center. We're going to talk about this V4641, and we're going to talk about SS433, which is kind of nestled in here, and I probably won't get a chance to talk about the cocoon, but it's really interesting down here. So we see there's lots of interesting sources, but and we know most of these things are pulsar wind nebula, and we'll talk about what some of these things are, and we'll see them in other maps. But okay, so if we look at the highest energy map, and we look at, let me just concentrate on the lower plot for a moment. We look at extended objects at 0.5 degrees analysis. We see above 56 TeV, we see approximately 25 sources that produce gamma rays above 56 TeV. Okay, a number of these are things we'll call TeV halos. We'll talk about them. But most of these high energy sources appear to be extended. And that's really interesting. So if we look above 100 TeV, again on our extended analysis, we see about 18 sources above 100 TeV, okay, compared to 3 in past 4. And we can even go up to 177 TeV, where we see approximately 4 sources that are still producing above 5 sigma at 177 TeV. So to remind you, I don't think I said this clearly before, if I want to get a photon of 100 TeV, likely comes from an interaction of its hadronic, an order of magnitude higher energy, so a PeV. All right, and so that kind of gives you the scale of what we're looking at here. So these sources that we see in 100 and 200 TeV are really likely Pevatrons, things producing particles at a PeV. So one of the more interesting things we discovered, and sort of shocked people when we first discovered it, we actually first discovered the source Gaminga with our previous generation experiment, Milagro. And the thing that's interesting, this is looking at the galactic center. Now, the touchstone for all gamma ray astronomy is the Crab Nebula. And the Crab Nebula is a point-like object. But when you look at this picture, it looks like this big blob. That's because you're looking down on almost 300 standard deviation Gaussian. So when you look down on it, it's got a big footprint, but it's a point-like object. We see some other things here, this thing we call the Crab on Fire, these other TeV, but these things, Gaminga is this giant middle-aged pulsar. I like calling something that's a few 100,000 years old middle-aged. It makes me feel young, okay? But it's a pulsar wind nebula that the size of it is enormous. The TeV gamma ray size is enormous compared to the actual pulsar wind nebula. The pulsar wind nebula is a few pixels across on this graph. What we see is gigantic. We also see this thing monogem, which is just like it, also enormous. This thing is the width of this is 5 degrees across the sky. I mean, this thing is really enormous. So what we discovered, when we looked at this thing, we said, what is doing this thing? And somebody labeled these things TeV halos. Because what they are is the TeV, well, first off, all of the sources we see are likely associated with things like pulsars and that kind of thing, but they're not produced directly by the pulsar. Pulsars do not produce 30 TeV gamma rays. What they produce are shocks that hit the medium around it, and stuff is accelerated in the medium around it. So while they power these things, they don't produce them directly. They're produced in the region around, in the pulsar wind nebula around it. In some cases, in these middle-aged, older pulsars, the electrons have escaped from around the pulsar, and what we're seeing is them interacting in the interstellar medium around the pulsar. So the idea is that these things, and so here are 2 nearby ones. So the idea is that what you have originally is you have a pulsar wind nebula that, because of its magnetic field, is confining electrons, but as it gets older, some of these electrons escape and they interact with other photons in the surrounding region. And here's where it gets a little teeny bit tricky, because the highest energy electrons, because of relativistic effects, can't interact with visible light or even IR, because the cross-section drops once the center mass energy between the electron and the gamma ray gets to the electron rest mass. Relativistic effects as the cross-section starts to drop off. So the only thing you can interact on at really high energies are really low energy photons. And the really low energy photons that are out there and pervade space are the cosmic microwave background. And the good news is we know exactly what it is, because for all the wiggles and all the stuff they show you with the CMB, it's really flat. You know, they're showing you 10 to the minus 5. We don't care, it's just flat. So the idea is these objects were called TeV halos, and here's a plot that I found yesterday from one of the talks we had at HAWC. So in the early stage, when the things are like 10 kiloyears old, the electrons and positrons are confined in the pulsar wind nebula. As the thing gets to be 100 kiloyears old, stuff starts to diffuse out into the interstellar medium, and by the time it gets much greater than that, the pulsar wind nebula is here, but the electrons are interacting in the interstellar medium around it. And that's why we're seeing these things which we call TeV halos. And they were basically discovered by HAWC and Milagro, and now we're able to measure them in PASS-5 really well. We can measure the diffusion coefficient of the electron, how the electrons diffuse away from the source. And we can see them from this is Dominga, this is Monogem, and here's another one of these things. We've seen many, many TeV halos, and nobody expected them. And they were a bonus for us for the following reason. Those Air Cherenkov telescopes with the things, they have really good angular resolution. I mean, really good. But that helps them a lot for point-like objects. Fortunately, most of the objects aren't point-like. So having a little worse angular resolution doesn't hurt you. So anyway, that's kind of where we are. Another interesting thing, micro-quasars. So I'm old enough to remember what the origin of the term quasar comes from. Okay, when I was in undergraduate school, they discovered these things which were really bright, but they didn't look like stars because they didn't have spectral lines. So they called them quasi-stellar objects. And it's quasars. We now know that most of these quasars are active galaxies. And active galaxies are other galaxies. They have supermassive black holes, 100 million mass solar black holes, and they're other galaxies. Most galaxies have some of these things, but a micro-quasar is like having one in your own lab. Well, not quite, but in your own galaxy. Okay, and what it is it doesn't have a supermassive black hole. It's got a 2 or 3 solar mass black hole and a companion. Instead of an accretion disk from a galaxy feeding it, it's got a companion star. And so micro-quasars have been known for a while, okay? And one in particular is quite interesting. So this one called SS433 has been seen in X-rays and other things before. And we have seen micro-quasars where, like real blazars, the jet points to you. But the thing interesting about SS43 is the jet doesn't point toward us. The thing is almost sideways compared to us. So we looked at this object, and so here's the direction from the Earth, and we're looking at this thing, and the jets are going out sideways. And what we saw was high energy gamma rays coming from where the jets interact with the material around it. So the thing that's really interesting about this stuff is that these are not Doppler boosted jets that are pointing at us. We're seeing acceleration in this regime where this jet comes crashing into the material around it, and there's a Fermi acceleration going on as you compress the jets, and we're seeing this high energy TeV gamma rays produced. The micro-quasar in this picture up here, up here is here. The 2 gamma ray sources are here. And what's interesting is this is similar. Fermi, the satellite, has observed similar things in some galaxies like Fornax and other things. So this is a really cool process. So we wrote a Nature paper, for what that's worth, back in 2018. But now, one of the problems of detecting this thing is it was really close to another big bright source. So here's this big bright source, 1908 plus 06, and here is the 2 jets of the micro-quasar. And so we have to model this thing to get rid of it. And when we do, we can look at this and we can compare it to the radio emission, which is here, and we see that what we see is this jet being accelerated there. This has later been confirmed by other experiments, and it's really quite interesting. We are now in the position to measure the spectra of the jets. And so we can actually look at the spectrum and see that they're fairly hard and very similar to each other, the 2 jets. And, okay, so I'll just, go back a second. Anyway, so the answer is we're able to study these things, and this was the first discovery of this kind of a micro-quasar. We recently saw another micro-quasar, okay, and it's newly discovered, even though it's really gamma ray bright. And you're kind of like, well, how did we discover it and nobody else saw it? So the Air Cherenkov telescopes have been studying the galactic plane, the region around the plane, because they have to point, and they have to study. And if we go back, and I'll come back to this slide in a second, if we look at this, notice that this particular object is well off the galactic plane from our point of view. So they just missed it, okay? But again, we're able to go back and measure this thing, And we have now measured the spectra of this thing out to beyond 200 TeV. There is no evidence of a spectral break. And since electrons are likely to have a spectral break or a cutoff, this is likely that we're seeing protons accelerated in the region around this micro-quasar. So, pretty cool. Okay, we also look at other kind of binaries. So the micro-quasar is, you know, it's got a jets and this, but here, for example, is LS 5039, and it's got it's a main sequence O star here, a heavy one, massive, okay, and it's surrounded by what's likely a black hole that orbit each other every 3.9 days. And we can see it tucked in by this other source right here. But with PAS5 and good angular resolution, we can model this source out and just watch it. And we have this multi-source fitting procedure. And we can now actually look quite well at the spectrum of this thing, where when it changes from the inferior conjunction, when we see the thing closest, let me go back. Sorry, I should have said this before. So you can see here that there's inferior conjunction is when the black hole is toward us and the star is back here, and the superior conjunction is when the black hole is away from us. So what we see with this source is different spectra, and the source with the inferior conjunction with the black hole near us is much harder than we see for the other source, which is the inferior conjunction. So we're able to start to measure this and understand the acceleration process. See what I'm doing here. So another thing which we've just recently are in the process of reporting on is the galactic center. Now you think to yourself, that would be the first place you might want to look. Problem is, the galactic center is in the southern hemisphere. And the galactic center is at peak, it's at almost 28 degrees south, so it peaks at 40 or 27 degrees south, so it peaks at about 48 degrees zenith angle to us. So we're looking through a lot of atmosphere. And our PAS4 analysis would not let us look there. With PAS5, we can see quite clearly the galactic center, okay? And we see the emission along the plane, which we're modeling, the diffuse emission, which comes from protons interacting with other things in the material, and we're able to study the source at the galactic center, which we see goes up to at least 70 and probably well over 100 TeV, which the Air Cherenkov telescopes have observed, but never above 35 or 40 TeV, because they can't spend a long enough time on it. So we look at the whole overhead sky every day. And so the reason that HAWC can see much higher energies than anybody else can see, except another experiment like us, is that we are looking at the sources, their entire visible sky every night, all of them. Okay, so let me kind of, there are other Pevatron candidates, I think I'll skip on that. Let me tell you about something weird. Okay, it's because it's fun. And that'll probably be the last thing I really talk about. So in 1990, Dave Seckel, I know, and Todor Stanyev and Tom Geiser, Todor and Tom were just giants of the understanding cosmic rays, had this weird idea that maybe cosmic rays would come in and, aiming toward the sun, would mirror back from the sun. So as you probably know, if you have a converging magnetic field, as a particle comes in, it spirals along that field, but as the field gets stronger, the pitch angle gets higher, and then eventually it bounces back. That's what bounces the particles back in our radiation belts. Okay, that's why the roar and all that stuff. So they had this idea that cosmic rays of a certain energy might go toward the sun, bounce back, and interact pointing toward us on the way back. And they were interested in neutrinos and came to the conclusion it wouldn't work for neutrinos, but they said it might work for gamma rays. Well, that's what we're looking for. So the idea is that the cosmic ray comes in, it mirrors, and when it's coming back out, it interacts in the corona coming toward us. Now, the problem is, first off, it's kind of interesting that both the moon and the sun provide shadows for cosmic rays. So if you think about it, cosmic rays are coming from everywhere, and the moon's up there and it blocks cosmic rays. So one of the first things you look at with an experiment is, can I see the shadow of the moon? But the sun blocks them too, up to a certain energy. Below a certain energy, it doesn't block. Below a certain energy, it doesn't block them because they mirror off the sun, and you've got it's like having a white ball in a white room. You can't see it. But at high energies, they are absorbed by the sun, and the shadows are always shifted a little bit. The reason is the shadows are protons mostly and nuclei, and they're bent by the fields, the Earth's field. So we see them offset as a function of energy, but we see an offset. But the gamma rays produced by this are not offset. So what we can do is we can verify, we can look at the sun, and the sun's magnetic field varies according to the 22-year cycle. Okay, so we can subtract the shadow of the sun and look in the hole where the shadow was for gamma rays. And what we see are gamma rays right at the spot of the sun. And we see this gamma ray excess, and it has just the characteristics you would expect for our angular resolution, and it only works. So let me remind you this: solar max is the time when there's the maximum sunspots. Solar min is when and solar max has the minimum magnetic polaritomagnetic field. So think of max as the lower field and min as the higher field. And so what we see is there's a difference between when the field is weak and the stuff doesn't mirror well, and strong when it mirrors well. We can look over the 11 years of the changing cycle. And we can even see that at high energies, the stuff goes in too far and hits the sun. So this is a kind of weird but interesting result where we can see the cosmic rays mirroring off the sun. We can measure the spectra of these two things, and we see that the solar min, which is the higher field, has a harder spectrum than the solar max. And we are now, it's kind of just an interesting result. So let me pass on AGN for a moment because we don't really have time. And I will mention that we were very unlucky in one way, that the brightest event that ever occurred in a gamma ray burst occurred over our competitive experiment in China. And we were on the other side of the Earth. And so while we would have seen it like crazy, our field of view was here. The thing happened there in Lasso's field of view. Anyway, we didn't make a significant detection. I'm going to pass on some of this and point out a couple things. That we now have outrigger detectors, which are these smaller counters, which allow us to identify for higher energies where the core hits outside of our array, which allows us to get good angular reconstruction. So we've been building these things, but and this is the picture with the outriggers in there. You can see all the outrigger dots are 350 outrigger tanks. But unfortunately, a year ago, February, something bad happened. There was a brush fire, and the brush fire swept up the mountain and swept through part of the outrigger array. Now, there's an experiment I have done with my 7-year-old grandson where you take a balloon, you can try this, you can actually do this too. You can take a balloon and fill it with water, put a flame under it, and it will not burn. You can boil water in one of these things with a flame, because the thermal capacity of water. On the other hand, the cable's burned. So we lost a lot of outriggers working. We're in the process of replacing the cables. But I did get a chance to talk to the National Science Foundation and tell them a line from a Billy Joel song which says, "At least we didn't start the fire." Okay, I mean, the best I could do, okay? But anyway, we're coming back from that. You can see how the outriggers, the one that looks charred, the outrigger wasn't charred. It had a black cover over it that was charred. But the fire was kind of bad. And here's my balloon experiment over here on the right. Okay, and interestingly enough, the area that came back, this was taken a year ago, just next month, the area that's green is what burned. Because these plants are funny. So they come back green and then they turn brown again. But we're in the process of recovering. And I will tell you that the next thing, the last two slides are this, that the future experiment, and we just had a meeting here in Mexico City about this, is called the Southern Wide Field Gamma Ray Observatory. And the idea is to build a larger scale detector like this in the Andes, where you can view the southern hemisphere. And so we're working on that proposal right now. And as part of that, we took a number of people up to the site on Saturday. And so this was the picture from Saturday behind a bladder we inflated. So you can see a number of us standing there. And so we had a chance to show them what the site is. And this is what the future will be, is this. So let me end with that and take any questions. Yes. Yeah, oh, microphone.
Okay, so it's time now for questions. So we are going to start here at the auditorium, and then we go to Zoom.
Perfect.
So first question here.
Well, my questions are always of ignorance. Now, when you...
It's on, just talk loudly.
Okay, can I... Closer, I can... Do I eat it?
It's okay.
Do I eat it, or what do I do with it?
Okay. Maybe a different one. Try that one.
Okay, my question is the following. What is the... I mean, you have the observations permanently. They go around every year, every day,
Yes.
whatever. For example, all these results, what is the accumulated time that you have for them?
Okay.
Or, so are you accumulating 10 days, 3 years?
No, we
20
have
years?
at this point, we started officially in March of 2015, so we have 9.5 years of data.
Yes, but is it accumulated?
Oh yeah, we have 10 petabytes of data at the University of Maryland, and we have 10 petabytes here at UNAM, okay, at the Instituto Nuclear. I mean, so 10 petabytes of data. And so one thing about this experiment is it's archival. If someone says, what happened on this day in 2017, we can go back and look.
Yes, but my question is slightly different.
Okay.
To bring out these results, these images or these sources, do you have a 1 month accumulation of data, or is it 20 years accumulation?
It's the 10 years of data.
Okay.
All of it summed together. Okay. Because we're just continually accumulating, building statistics. Because we are again, our statistics are how many events versus how many background. And as you go longer in time, you do better. As the background increases, there's the square root of the background versus the signal, so more time, more signal.
Thank you.
We go with another question here at the auditorium. Is there any other question? No? On Zoom or in Ensenada? Okay, we have another question here then.
Yeah, thanks, Jordan. Very nice seminar. The image that you had at the beginning of the sun, the neutrinos from the sun,
Yes.
was slightly elongated.
It was
like
what?
oval, elongated.
Oh.
Why is that?
No, it's just the
you have an
coordinate
idea?
system. That was just the coordinate system. I mean, it's, again, it's kind of a cheat because when you look at this picture, and I didn't make it, but Bob Svoboda made it, but it's a very famous picture, this picture of the sun from underground. To give you an idea, the sun is like 1 pixel in this. The neutrino resolution is terrible, okay? But there's nothing else. That's just the coordinates. It picks whether you get the same, the sun, if you have the same declination, it gets elongated. But no, it's consistent with round.
How many accumulated?
That, I think, was about 5 years of Super K data. I mean, so they get about 15 neutrinos a day in Super K from the sun. Okay, and again, the angular resolution is terrible because they're 7 MeV, they're MeV neutrinos, so they don't carry a lot of punch.
Any other question here on the room?
Back
Over there. Yeah, good.
Hi, Jordan. Nice talk. I would like to ask, which kind of feature do you expect with SBIGO for the next generation of gamma ray telescope? You expect made some discoveries like HAWC, or you expect I don't know, discover something more significant in the sense of I think that the capacity of SBIGO bring us better sensitivity than HAWC, no?
Yes. So one of the things that we hope to be able to do with SWIGO, which is different than with HAWC, is by being in a higher elevation and having better low energy sensitivity is to be able to track more gamma ray bursts, for example. But you ask a really difficult question, which is, what do you expect to discover? The problem is, we didn't expect to discover 90% of what we discovered. No one predicted TeV halos. No one predicted we would see micro-quasars. All these things are, and we're still discovering new things all the time as our graduate students plow through the data and they go, wow, this is really weird and interesting. Okay, and so a lot of times it's hard. We will certainly be able to probe the galactic center better. We'll be able to work with CTA, which is being built in the south, to help them target, to have a wide range of observations. But the whole point is that we will have something that looks for the first time in the southern sky. And we'll discover all kinds of potentially new objects that we haven't. But, it's hard to believe the galaxy is very different from one side to another, but we've seen a few singular objects like this this V4641 and other things like this. And so there'll be a whole catalog of new things, and then we'll discover new physics related to those. Because a lot of times this stuff makes sense if you don't have great data, but if you have really good data, then it doesn't make sense, and that's where you learn new physics.
Okay, so another question here.
We have looked for the Magellanic Clouds. At least we can see we look for the Fermi bubbles. We haven't seen them. The SWGO could potentially see the Fermi bubbles, and therefore the Magellanic Clouds, which are in the south, because they're Magellanic Clouds. So we can't see, but we've looked for molecular clouds, but the Magellanic Clouds, which are a galaxy thing, you should be able to see them potentially in the south, and more AGN as well. Yeah, yes, exactly.
Thank you very much for your very nice review on HAWC results. Could you mention something about the results on dark matter annihilation detection? There are some limits. Were you able to put some limits on the properties of dark matter?
Yes. So we've looked at a lot of, actually, there were a lot of things I didn't cover. Dark matter is certainly one of them. HAWC has some of the best limits on high mass dark matter. So one of the things you can do is that there are a number of, just fill people in, there are a number of dwarf galaxies that surround the Milky Way and are nearby, which have high densities of mass to light ratio. And these dwarf galaxies, we think, are very heavily populated with dark matter. But the nice thing about a gamma ray observatory like this is you don't have to point. You look at the whole sky, and if someone says, oh, let's look at Temecula, we can look at that thing, and we can even sum them. And so the fact that we haven't seen gamma rays coming from what would be a not visually bright object has been able to set some limits. So we have set limits on dark matter in different channels, in TT bar, BB bar, and those kind of things, and we've written some papers. We've also set limits on, interestingly enough, Lorentz invariance violation. So different models of Lorentz invariance violation predict that photons above a certain energy might not propagate through through space. That they might effectively give it an effective mass for the photon in space-time, and what that would do is allow it to decay. And so the fact that you can see spectra that extend beyond a certain energy to a certain distance sets limits on Lorentz invariance violation. So we have, that's what's kind of great. You have this great data set. We have some really smart graduate students and postdocs, and they're going and looking at all different things.
A second question, where is WIWO will be installed?
Yeah, let me know when you figure it out. We're still arguing over it. So we have 3 potential sites. We have the site near the Atacama, okay, near Alma is one site in Chile. We have a site in Peru, okay, and there's a site in Argentina. And we're discussing the pluses and minuses. And I would say that one of the things that I've learned as a person who was involved in this and dealing with it is the critical role that the institutions in the host country play in building an experiment like this. So we had the advantage of UNAM and Inouye, where people, Arturo can drive up and fix things, okay, and knows stuff. Everybody here knows how to, the postdocs and all here work on the experiment. The lab at Inouye provided a structure that we had. And so one of the things we have to consider with building a next generation detector is we from the outside, from Europe and the United States and other places, can't just go to a country and do something. It has to be supported by a strong infrastructure in the country, which is one of the reasons we chose this site to build. You know, when I was here in 2006, we talked about it and realized that the site we were between UNAM, which was the biggest university anywhere, and the lab and having the LMT, all those things allowed us to build this thing and be successful. And we could not have done it if we were just trying to do it from the outside. I mean, you could build ALMA because you had $1.5 billion, but we're not going to have that. Yeah.
Hi. So I have a question regarding SWGO. Will HAWC and SWGO work together?
Great question. So, I mean, look, you know, there's the thing that fuels all of this at some point is money. To be honest with you, HAWC isn't very expensive to maintain. The most expensive part of HAWC, far and away, I mean, way more expensive than anything else, is the data. Keeping 10 petabytes of spinning data moving, and you know, you don't think about it, but even if you stopped today, so we're not going to get a day's worth of data, you still have to buy a lot of disk, because disks have a 5-year time scale. Okay, so yeah, that's what's part of that is, so we're trying to figure that out. How long can we operate it? How can we afford to do it? You know, and how long is the detector going to run? There's no reason it can't keep running, provided it doesn't catch fire or something, a volcano go off. I don't know, things, you know, beyond your control. So I don't know, maybe, I think it would make sense, because it would make sense to have coverage in all the hemispheres. So we have east coverage now with LASO, we have west coverage with HAWC, and in the north, and it'd be nice to have coverage in the south at the same time. Will the agencies pay for it? Do we have the people? I don't know.
I have a question related to the data.
Which?
The data. Yeah.
Data.
Yeah, when it's going to be like available to the public in.
Another hard question.
Manuals or something too.
So we would, keep, you know, the National Science Foundation, I'm sure something comparable in Mexico, says your data should be public. But, you know, it's not like you can make 10 petabytes of data public. And you know, Fermi satellite has done a magnificent job of making their data set public. And they have a crew that's the size of HAWC that works on making their data public. Okay, because they have people and it's paid for. Whenever you ask for money from the National Science Foundation to put money into making your data public, they say, great, we can cut this out of your budget when we're cutting your budget. But you should do it, but we're not going to pay for it. So we would love to, so one of the things we've talked about, and this is actually a really great question, is in our next operations proposal, doing some things to really make we already have some data public. Our 3 HAWC catalog is public. We're going to make our 4 HAWC catalog public. We want to be able to do some things where we provide tools for people to get at our data. We're not going to can't make the whole data set public, but we can make the results public and let people probe them themselves. And that's what we're trying to figure out how to do. But I think it's a great thing. It's a goal we've been working toward. We have yet to be really successful. Again, you can go on and the 3 HAWC catalog is on there and you can probe it. But, you know, I got an undergraduate who's helping me do some stuff that maybe we'll be able to put online, but we'll see.
So we have one more question over there.
Okay.
A very nice talk, thank you. My question is what kind of information you get from a binary neutron star merger, say GW 1708?
Yeah. So the answer turned out to be that it wasn't in our field of view, okay? We would have loved to have been able to see that thing, but it didn't rise till about, I think 8 hours later. So, and it was pretty low in the horizon when it did rise. So we're working here at UNAM, we're at the Institute for Astronomy, we're working on a result that says potentially we may have a gamma ray that we can associate with that event. Fermi, in space, sees an event just about at the same time, not exact time, but 8 hours later also. And so, but we should be able to see a kilonova if it's close enough. The thing is, that was a very close kilonova. And depending on how on axis it is, you might be able to see it. But we would one of the things that people, honestly, one of the reasons they want us to keep running, to answer your questions, or to answer your question, is to be there for the next binary merger. Because you'd really like to see it with a gamma ray telescope. And again, you don't have to point ours. If it comes overhead, we'll see it. So, and the fact that LASO saw this gamma ray burst so brightly, I mean, it would have, blown us out of the water had it been over our field of view.
And after the event, you haven't been able to see anything else, or?
No, not since then. I mean, we don't see the source at all. No. Okay?
So one more
Analytic.
question. Yeah.
If you could pick the next HAWC result, new result, what would you like it to discover?
I would like a gamma ray burst right over top of the experiment. Okay, that's what I'd like. So if you can arrange it, please.
Okay, so I think it's time to finish the colloquium today. So we thank Jordan. Here I deliver you a certificate from the Institute.
Okay, thank
and
you.
a small present also. So
Oh,
thank you
thank
very
you.
much for
Thank you.
coming today and to give this fantastic colloquium here. We
Sincerely, my
can thank
pleasure. Thank you very much. My pleasure.
the speaker now. So I have two announcements before closing everything. The first one is that we are going to have lunch now with Jordan, and we still have some places for the people who want to join us. We are going to go to 97 here at the university. And the other announcement is for the students, so don't forget that at 4:30 we will have an informal conversation with Jordan, so you can ask also him or talk with him about the academic life in general, some questions that you may have about your career or about his experience, and it will be here at the auditorium at 4:30. So everyone is welcome also. Thank you very much, and see you later.
Thank you so much. This was great.